Hi. In the last couple of videos, we covered linear version of ISLM and ASAP model. So, I told you that actually using the linear version of the model is not that easy because there is so much that we need to calculate. You know, the determinants we need to deal with are usually rather complex. In order to make those calculations simpler and in order to actually incorporate nonlinear relationships between the variables, we can actually move to general functions. And this is where we're slowly going to be moving since today. Now, first thing that we need to introduce before we can actually solve those new versions of the models are total derivatives. So, what is the total derivative? Look, imagine a case like that. Y is a function, some function of two variables, x and w. We know already how to calculate total differential of this function, and we also know how to find all the partial derivatives. However, there is one thing we haven't considered yet. What if x is also a function, let's just say g of w. Okay, so look, what do we actually have in here? X and w influence y. However, w also influences x, that in turn is going to influence y. How can we capture all these relationships? In order to do so, we create something that we call channel map. Okay, and what is our channel map? It will show us how x and w are actually influencing y. Because look, what do we know? We know that x is influencing y through function f. Right? X is over here. This is clearly what we see. We also know that w is influencing y through function f. Right? So, basically, this is the kind of story we were discussing before. But now we've got something new. Look, what is happening over here is that we also see that w is influencing x through function g, and then in turn it influences y through function f. So look, this is why we call this channel map, because we see different ways in which, in this case, we can say solely w influences y. How? Look, we can say that we've got two channels. First one we would call direct channel. And we see that through direct channel, through function f, w impacts y. However, we also see that w influences y indirectly. How? Because first, w has impact on some other variable like x, and then this variable directly influences y. So in this case, because of this intermediate step, we call it indirect chunk. Okay, so how do we assess impact of W on Y if we want to know its entirety? Look, we can think about this function y f of xw as some different function. Let's call it, well, it's still going to be f, but we can write it as g of w, which is equal to x and w. Right? And look, knowing this, we can easily actually assess this impact as long as we remember about all the necessary steps we need to take. Okay, of course, we're going to start by calculating total differential. Right? So, our total differential is going to look like this. This is going to be dy equals to. What do we need to influence in this total differential? Look, we need to, of course, assess impact of all these variables on y separately. So, partial derivative of y with respect to x times dx plus partial derivative of y with respect to w times dw. Okay, let's introduce some shorthands because those formulas can get very long. So let's just say that dy dx, we're going to call fx. Right? dy dw, we're going to call fw. Now, do we have any other partial derivatives over here? Actually, we do. The one more partial derivative we could estimate over here, we could calculate over here is dx dw. So impact of w on x. Okay, so let me rewrite this in the new form. So we will have that this is fx dx plus fw dw. Now, what we have now is the change in y. However, we want to know what happens to y as w changes. Then what should we do? Look, if we know that w actually changes, it means that dw must be different than 0, right? And if dw is different than 0, what we can do over here is to divide both sides by dw. And look, what we get as a result on the left hand side is derivative dy dw, and over here we've got fx dx dw, right? Plus fw. And look, what you see over here is a formula for total derivative. Total derivative can actually allow us now this is very theoretical, so let me just give you a very simple example. Okay, so we've got that y equals f of xw is equal to 3x minus w squared, right? And now let's say that x is equal to some function of w, and it's equal to 2w squared plus w plus 4. Okay, so look, of course we could do it right away, and once you get, let's just say, more familiar with the procedure, you will be able to do it right away. But first, let's calculate all the partial derivatives. So look, we would start with dy dx, or fx. We differentiate this with respect to x, we get just 3. Okay, now we differentiate this with respect to w. Fw, we get this is negative 2. Right? Okay, and then we calculate the last derivative. So dx dw, and we get that this is 4w plus 1. Okay, so now let's calculate the total impact of w or y. Okay, let's do it in steps. However, as I said, later you can do it as fast as you can. So we've got that this is f of x dx plus fw dw dividing both sides through dw gives us dy w equal to f of x dx dw plus fw, and this is 3 times 4w plus 1 plus minus 2w, or simply this is 12w minus 2w, this is 10w plus 3. And look, if we know what is the value of w, of course we will be able to assess this variable. But this gives us a total impact of w, changes in w on y through direct channel. As you see here, the higher the w, the lower the y. And through indirect channel, we can see that the higher w, the higher the x, the higher the x, the higher the y. Here we get the final outcome. Okay, so let's now get one tiny step further. What do I mean by that? Look, the technique I just showed you has this advantage that it can be easily generalized in such a way that it can deal with channel maps of any degrees of complicity. But let's start small. Let's just say now that y is a function of x1, x2, and w. Now let's just say that x1 is some function of w and x2 is also some function of w. Okay, let's now construct channel map for this case. Look, we know that the source of change we want to consider here is w, right? So how does w can influence y? Well, it can do it in 3 ways. First, it can be done directly through function f. Okay, let's use colors to distinguish between the channels. So this would be this direct channel that we see over here. Yeah. We also see that W through function g1 influences x1 and then x1 influences y. So we've got first indirect channel where W influences x1 through function g1 and x1 influences y through function f. Finally, W influences x2 through function g2 and then x2 influences y through function f. Okay, again, I could easily rewrite this function as right? So again, if we apply everything here correctly, we should be able to find total derivative, right? So let's start with total differential. And first we see that this function can change as a result of changing x1. Let's just say that dy dx1 is some f1. So we've got f1 dx1 plus, of course, f2 dx2, where of course f2 is simply partial derivative of y with respect to x2. Okay, and finally, the third source of change is fw, is w, so we've got fw in the same way as we did before, dw. What do we do next? Well, of course, all we've got to do is to divide both sides by dw, and we should get the formula for the total differential. So this is the derivative, dy dw is equal to f1 dx1 dw plus f2 dx2 dw plus f w. Look, the only thing that actually changed over here is that now we have more components, but the logic behind what we did stays the same. Okay. Now let's consider an economic example on application of total derivatives. Okay, let's just say that we've got production function where Q, so level of production, is a function of 3 things: capital, labor, and time. Okay, you might say, why in the hell time is in the production function? Well, you can imagine it like that. As time passes, people figure out or discover new technologies. With new technology, we can use factors of production better, and with the same amount of factors of production, we can actually produce more. So think about this time in this context as a function, as representing state of the technology. Now, of course, as time progresses, number of people willing to work changes. So we can also say that labor is a function of time. And also, investment So purchases of capital goods also require time. So we can expect that with time, we will have more capital. Okay, so how will we deal with this case? Look, if I want to draw a channel map, it's pretty easy. We've got Q at the end, T at the beginning, and we see that T influences Q directly, and then T influences Q indirectly through labor and indirectly through capital. Okay, so let me just introduce to you one more thing that we will be using in the future, not in this class, but in the future we will be using it a lot. This is a derivative of a variable with respect to time. This is so-called time derivative, and we usually write it as a Q with a big dot over. Okay, so look, let's write now the entire expression for this derivative right away. So we're going to be using this one, right? So first, we need to get derivative of Q. So let's write it here. That's. Remember, this is dq dt. So we already have this thing. Those are in the same form. So we need to get partial derivative of Q with respect to capital, right? So we call this derivative, as I hope you remember from microeconomics, marginal product. We should say marginal physical product of capital, but I don't want to make it too long. Product of capital. By this, and of course, this is multiplied by derivative of k with respect to time, right? So we could just write it like that, right? That would be d k d, right? Is by definition written like that. Then we've got plus, and we need to do the same for labor. So first we put QL, and QL is simply derivative of Q with respect to labor. So this is marginal product of labor. And we multiply it by time derivative of L. So again, okay, what is the one thing missing? Well, we miss derivative, partial derivative of Q with respect to time, right? So this is, right, which we will denote as QT. And look, this expression that we found over here is showing us what is happening to the level of production over time, taking into account all possible chunks. if the situation is even more complicated than this. And to do so, we just need to modify what we learned slightly. And we're going to move to a very oxymoronally sounding name, because we're going to do something that is called partial total derivative. I hope you can see the oxymoron in those two words, because on the one hand we've got partial, so just part of something, on the other hand we've got total. They might seem conflicting, however, once we explain what do we mean by that, it becomes pretty much obvious. Okay, so now imagine a case like this. Y is a function of 4 different variables. x1, x2, u, and v. Now, of course this is not it. Let's just say that x1 is some function of u and v, and x2 is some function of u and v. Okay, again, what we need to do is to draw a channel. However, I hope you can see right away that over here we will have 2 different sources of change. Okay, what do I mean by that? Look, here we have y. Let's just say here we've got u, here we've got v. Okay, now what do we see over here? U can influence y directly through function f, right? Then u, can influence y indirectly through function g1 and by variable x1, and then x1 influences y through function f. And similarly, another indirect channel of influence of u goes through g2 to the variable x2, and then from x2 to y through function f. However, I hope you can see that at the same time I can conduct very similar for v. Look, we see that v influences y directly through function f, and then indirectly through x1, and indirectly through x2. Okay, so we see here that situation gets very, very complex. Okay, let me just notice one thing. Look, if I would like to write a total differential of this, I would get that dy is equal to f1 dx1 plus f2 dx2 plus fu du plus fw dw. Look, these are all the possible sources of change in variable sources of change of variable y. However, we need to also take into consideration indirect channels, right? Which would make this thing very complicated. Why? Because look, if I assume, for example, that both du and dw then what should we do with it? If I divide both sides by du, right, then we've got how much is that? Well, this is clearly probably 0, right? Probably. Well, actually, we are, and it should be V. I'm sorry, V, of course, V. And we do not know anything about the relationship between U and V. We can assume it's 0, right? So this component will be gone. And look, basically, this is the tree where we would go. However, look, if I know that W is changing at the same time, I should also divide both sides by dW, and then this component would be gone. So, what do we do to avoid this situation? We still calculate total derivative in the sense that we are capturing all the channels of influence, but it's going to be a partial derivative in a sense that we will assume there is only one source of change. So look, we are either assuming that du is different than 0 and dv stays constant, like in the entire idea of partial derivative, or we are assuming that dv is different than 0, and then we assume that du is different than 0. This is why it's called partial total derivative, because total means we get all the channels, partial because we only focus on one initial source of change. Okay, so how do we write this? Okay, look, expression for total partial derivatives are weird. Okay, first, very often we use articles. So here you have, let's just say we are starting with y, right? And with u. So impact of u on y while v is held constant. We would write it like that. However, there are different ways in which we can write it, because this is the same as dy du. We put the bar. This is total derivative of y with respect to u while holding v constant. Or we can simply also write like this, even though this is like relatively long, the dv is constant. Okay, you can use any three of those. My favorite is this one, so I'm going to be using this one. And okay, now let's calculate in here impact of u on y. So we got d y d u d v equal const, it equals to 0, and it's equal to, first, partial derivative of y with respect to x1, so f1, times derivative of x1 with respect to u. Then we've got plus another indirect channel, x2, derivative of y with respect to x2 times dx2 over dv. And finally, the direct channel, so fu. Okay, and look, by the same token, quite easily, what we can do is dx1 dv plus f2 dx2 dv plus fv. Okay, this is it about total derivatives. You're going to be practicing them during workshops. And what we learned just about now is enough for us to make one more leap. This one more leap is implicit function theorem that we're going to discuss in the next video. Thank you for your attention. Take care.